30 seconds, sorry. That's perfect.
Let me start asking if you have any questions about what we talked about the previous two lectures. I hope you could. Also, I hope you could finally comply with the advanced simulation. Maybe later I will show we can share the results. So if there are no questions, I would like to talk about today is where the space-time is not vacuum. So not only black holes are there, but also stars, neutron stars, and disks, and so on. And this is a whole series of new difficulties in simulation, which are not unique to numerical relativity, but still we have to tackle them. And I would like to give you a feeling of how we do that. So, if the space-time is non-vacuum, we have additional equations. We have a stress energy tensor of matter, and we have conservation of energy and momentum in this equation, conservation of baryon number in this equation. And of course, these are the general relativistic equations. And we also need an equation of state, a relation between the hydrodynamical variable, pressure, resonance density, velocity, internal energy. This relation between them is related to the microphysics, and it's not something that, well, it's something that we have to insert into the simulation. It's not in the Einstein equation, it's not in the hydrodynamics equation. These are examples of the most simplest equation of states that one can think of. So the pressure is the power of the density, for example. So, in order to solve equations for fluids, we have to talk about shocks. And let me switch to a different software. Okay. So we have to talk about fluids. What are fluids? Probably you're familiar with that. They're a set of fluid elements, and fluid elements are pieces of volumes containing matter, such that the typical size is much smaller than the macroscopic system that you want to study, the neutron stars, the diffusion disk, of course, so that each of these volumes can be just considered as one point in your simulations and 1 point in your theory. On the other side, these fluid elements must be larger than the collision mean free path of the particles that they are made of, whatever they are, so that the values that we assign to a fluid element represents well the average of physical quantities of the particles contained in this small volume. Density, energy, and velocity. This is standard interpretation of fluids. And then I have to talk about shocks, because they do happen when matter is present. What are shocks? Shocks are arbitrarily large, arbitrarily localized spatial variations of the hydrodynamical variables in space. Right? So we can simply speaking, we can say they are discontinuities. So there is a jump in pressure somewhere. For example, two stars collide. There is a jump in velocity, okay? And often treat that as a discontinuity, mathematical, even if physically it's probably not. Matter is continuous, but these gradients are large and the space extension is so small that we can treat them as discontinuity, and we call them shocks. These are shocks. And hydrodynamics equations allow for the formation of shocks even from smooth initial data. Here is an example of a very simple equation called the Burger's equation. And the initial data we started with in this graph is this very smooth curve, and after a few steps, a shock has developed. This is a property of the equations, and the hydrodynamic equations do allow for shocks. So we have to use methods that can describe shocks, they can predict shocks. And these methods, I will describe now, that defines all your methods and concept systems. Let me also introduce to you a little about the difference between finite difference methods and finite volume methods. I don't know if you're familiar with the solving equations, partial differential equations numerically, but yeah, let me introduce that briefly. You can think, when you have a continuous function which represents your hydrodynamics, with density, pressure, velocity, and to the computer you can specify only some points, the grid points, so it becomes a discrete function. And there are two ways of doing that, at least. And if you think that the red points are your grid, now forget the lines for a while, and then you just say so the pressure, I know the pressure at this point, at this point, at this point, and so on. I don't know what's in between, but yeah, that's the discretization. And when this is time 0, and this is, let's say it's a bit different time, if when I want to solve the partial differential equation, d over dt equal something, d over dx, then I do the finite differencing so the d over dx becomes a finite difference between the value at this point, for example, and the value at this point. This will be connected and give the value at the next time. Okay, this is finite differencing. Another way of thinking of this is the finite volume way of thinking. So now we think that the point, the red dots, the grid points, are the averages of the physical quantities inside a cell. So now look at this picture as made out of cells. And so this point is the average, some average of the physical quantities inside of this cell. And what is different in the way of thinking is that in order to update to the next time, we can use the fluxes of matter through the cell boundaries. So it's easy to think of the density if this point represents the average density of the cell. At some time 0, at the next time step, this density will have changed according to how much flux of density has entered from all sides, from this side or from this side, and how much flux of density has gone up. Right? Does it make sense? Right? Okay. So these are two ways of thinking the discretization. And this is written in words, what I've already said. So finite difference is approximate the solution using finite difference, of course. And finite volume instead define these grid cells of finite volumes with average quantity, which are like an integral, average integral over the cell and deduce these quantities for the evolution by computing the fluxes, using the fluxes. So each time step, the update of the value of the grid cell is obtained using the flux to the cell boundaries, or some approximation to the flux. And why is this? This is, okay, final volume methods are very useful for solving hydrodynamic equations, because, as you can easily imagine, the fluxes sum up to, so if some matter goes out from one cell, it goes into the other. So matter quantities are conserved, mass is conserved, unless of course something is coming from outside the grid. If there is some source then from outside, then mass is not conserved, but it changes, increases or decreases physically according to the external input. Okay? This is very important. If mass is not preserved, then your code is not doing well. Okay? The neutron stars loses mass just because of numerical reasons. That's not. This is something new. We didn't have this type of constraint in vacuum simulations. Now, let me introduce to you conservative systems. We take homogeneous partial differential equations. It's a generic. This is written in a generic way. And but if we can write it in this other way, okay, so if we can take this function of this matrix in more dimensions into the space, okay, then we can call this a conservative equation, an equation written in conservative form. Why do we say that? Because the update of the variables u depends only on the fluxes. How the function f flux changes in space. So it conserves mass, for example. And so by extensions, this form of the equation is called the conservative form. Okay? And okay, now let me introduce to you also another concept, that of weak solutions. That again we have our partial differential equations, conservative system, and we have talked about shocks. Shocks, I said we treat them as discontinuities, so derivatives are not defined, so this equation is not defined if there are shocks. So what do we do mathematically? What do we do? We integrate it. We integrate this equation in space, and we get a different equation that is valid also for discontinuous solutions, for discontinuous functions. So it's also valid for when shocks are present. And the solution of this equation is called the weak solution of the equation. Okay? The solution, the weak solution to this original equation is the solution to the integral form of the equation. And I have introduced to you this concept because I will now show you a couple of theorems, that about conservative systems. And Wendell found that, proved that if a method written, if a system written in conservative form converges, okay? Convergence is a mathematical numerical property of that such that the errors of simulation increase with a given power when you increase the resolution. So when a method is written in conservative form and converges, then the theorem says that it converges to the weak solution of the equation you want to solve, which in our case is conservation of energy in domain. Okay? So this is a theorem. I'm not going to prove it, of course. And another useful theorem by Powell and Clark says that if a method is in non-conservative form, even if it converges, then in the presence of a shock, it converges to the wrong solution. That's a theorem. Okay? Not that it may happen, it really happens. Theorem. And this is put there to convince you that we really have to use conservative form for our systems. We cannot do without it. If you want to study matter, you have to write the equations in conservative form if we can. Not all systems can be written in conservative form. Okay, there are references if you really want to know the details. Okay, then let's go on and let's try to find some insight from the expression of the weak solution. Again, this is what I showed before, the equation that gives the weak solution. We can take inspiration from that to find a method to, numerical method to update, to solve higher dynamic equations. And yeah, this immediately comes to one's mind. The time derivative that was here has been made finite difference. We have t n plus 1 here, and it's equal to the solution, the average solution, integrated solution Tn plus the difference of the fluxes. And indeed, this can be written in compact form like this, with the definition of this capital F. And this capital F is called the flux function, and different conservative numerical methods different in the way they specify